Hello everyone, welcome back to the channel. This is Chem 2B chapter 10. This is the first part of chapter 10. Unlike the first chapter, I'm going to be splitting it up into 3 different videos to make it go by quicker. I'm also going to be explaining the processes quicker and not going as in depth, just going to the surface level of what you need to know. So the videos are faster and just better and easier to go back to when you just want to review. Okay, we're going to be starting with spontaneous processes. So, what does spontaneity mean? A reaction being spontaneous, that means that the basic definition of it that you're going to hear in class is it means the reaction is able to occur without outside intervention. And what that basically means is, I'm going to give an analogy to better explain it. Imagine you have a hill. You put the ball at the top of the hill. The ball is going to roll down, whether you kick it or it's going to roll down without any outside intervention. And when it comes to spontaneous reactions, the reverse of a spontaneous reaction is known as non-spontaneous reaction. And it's basically just the opposite of what spontaneous reactions mean. It means the reaction would not occur, or it needs outside intervention. And using the same analogy, instead of placing the ball at the top of the hill, imagine you place it at the bottom of the hill instead. The ball isn't going to go up the hill, which is the reverse of going down the hill without outside intervention. So you need to either roll it up, kick it up, or push it up. And that's the reverse of a spontaneous reaction. The other idea that I'm going to be discussing in this video is entropy. And what is entropy? Entropy is basically the simple definition. One word of entropy is disorder, disorderedness. So imagine it like a scattered room. And you don't have to fully understand what entropy means in this class, but for this class, what you have to know is you have to be able to identify when entropy increases or not. And basically, the change of entropy is the final entropy minus the initial entropy, just like the change of temperature and most other things you're going to see in this class. And how to know when the entropy is increasing. So luckily, the concept part of it makes sense. Like thinking about entropy as a disorder, it makes sense. And I'm going to list out the different factors that can affect the entropy of something. So the first one is the phase it's in, and the temperature, and then the moles or particles. They're both kind of synonymous in this context. I think I spelled that wrong. It doesn't matter. Okay, so when it comes to phase, the different phases there's the solid phase, then liquid, and gas. And when you think about it, in past class you might have seen this, but basically the atoms and the particles inside solids they're barely moving. They're not really interacting with each other. That's why solids stay in one place and they're compact. But then when these solids become liquids, they start to move around more. Like imagine ice. Ice doesn't really move around, but when you heat it up, the particles start moving around. They start getting quicker. The kinetic energy increases and the particles start moving more in liquid phase. And then finally, when it becomes a gas, that the velocity of the particles, they become even more. They start speeding up and moving faster. And that's why gas, it dissipates. Like when you release gas in the room, it's going to spread all over the room because the particles want to move away from each other. And liquids, they're kind of similar, but in between. In solids, the particles don't want to move away from each other. They're staying together. And you can use this idea to help figure out which phase has more entropy. So entropy is basically disorder, and gas is more disordered because it wants to spread apart. And think of it like a scattered room. Gas just wants to go all over and scatter the room, while liquid is in between and solid is the least. And then that is the first phase. And then when it comes to the second phase, temperature, it's the same. It's like similar. Like imagine, let's use water for example. The solid phase of water is ice, and then the liquid is just liquid water, and then the gas is vapor. As you heat up water, it goes from solid to liquid to gas. So if the entropy is increasing this way in terms of phase, and the temperature also increases this way, that means the higher the temperature, the more the entropy. And now moles, imagine it in this way as well. Moles is also increasing along with temperature because there's a lot more movement. You can kind of think of it in that way. More movement might be more moles, more particles colliding. So that means more entropy. Everything has entropy. So the more there is of something, that means it's going to have more entropy. So now you know how to define entropy and when it's going to increase or when it's going to be less. Now we're going to move on to the second law of thermodynamics. And you may be wondering why we're learning this, because this is a combination of the first law and the second law. So the first law basically says that, if you remember, energy stays constant. Energy isn't created or destroyed. And the second law is building off on that, and it's saying energy stays constant in the universe, but entropy is always increasing. And what this means is that, so for every reaction, what this means is that for every reaction that happens, the universe is a closed system. This is the entropy of the universe. It's a closed system, so that means there's no energy being created or destroyed in the universe, so it all stays the same. So imagine it being like in this box. For every reaction that happens in this universe where energy is transferred, the entropy is always increasing, because the reaction rate is never perfect. And a lot of the time when you try to transfer energy in between objects, a lot of the time some of the energy is lost as heat, and that increases the entropy as well. So that's just how you remember the second law, that the entropy is always increasing. And if you've taken a class like biology before, I think one of the bizes, the first one, and that they offer at UC Davis, they talk about trophic cascades, food chains, how when energy is transferred to food chains, only roughly about, I think, 10% of that energy is transferred, because the rest is lost as heat due to metabolic processes and stuff like that. It's kind of correlates with this, about how whenever there's an energy transfer, a lot of the time heat is lost as a result. And since the universe is a closed system, that means the entropy of the universe is equal to the entropy of whatever system is happening plus the change in entropy of the surrounding of that system as well. And when this entropy of the universe is zero, that means if you try to find the entropy of the system, you move the surrounding to the other side. So it becomes the entropy of the system is equal to negative the entropy of the surrounding. And this comes to play when you look at the equations of both of those things. So first, the entropy of the system is equal to the reverse. This is the energy, remember, the reversible energy over the temperature. And if you also remember from the last video, from chapter 9, the energy at normal temperature and pressure, it's also equal to the enthalpy, the change in enthalpy. So you will probably see this equation written with enthalpy instead of energy. And this is the standard form of the equation. It's the change in entropy of the system is equal to the change in enthalpy over the temperature. And since the system is equal to that means the surrounding is equal to the negative of this change in enthalpy over the temperature. Now that you have a broad understanding of the concepts, I'm going to try to show and do a practice problem. So with this problem right here, when you read the problem, the things that should pop out is what it's asking for, which is the delta S of the system, the change in entropy of the system. And if you remember the formula I just showed you right now, the change in entropy of the system is the change in enthalpy over the temperature. And when you look at the change in enthalpy, and another thing is when the change in enthalpy is a fusion, which is right here, that's what FUS means. Fusion is basically melting, and the change in enthalpy of fusion is saying the energy that it takes for a substance to go from solid to liquid, to melt from solid to liquid. And that's what this question is asking about. It starts with the fusion of ice, so it's going from solid ice to liquid ice at 0 degrees Celsius, which is the normal melting point of ice. So for this problem, we can see it's talking about 3 moles of the ice. And also another thing, pay attention to the units. The energy diffusion is given in units of kJ over mole. So that means you're going to have to get rid of this mole to find the kJ. And to do that, you just multiply by the 3 moles up here. So that's the first thing we're going to do in this problem. Enthalpy of fusion for 3 moles is 6.01 kJ over moles times 3 moles of the substance ice. And when you plug it into the calculator, it gives you 18.03 kilojoules. And now we have the change in enthalpy, so we plug it back to the original question here to find the change in entropy of the system, which is 18.03 kilojoules divided by, and for the temperature over here we're given the temperature in Celsius, but for this equation we have to use Kelvin, so we have to change the temperature from Celsius to Kelvin, which you just add 373 Kelvin. That's how you change it from Celsius to Kelvin. You just add 273 and it becomes 273 Kelvin. So you put it back in here, and this is the equation, and you plug it into the calculator to find the final answer. And that's the final answer. We're going to skip this problem because it's basically the same thing as the one up here, but the reverse in different delta H value. And we come down here, and I'm doing this problem to show that just like enthalpy can be calculated using these tabulated values, you could also see entropy, the change in entropy, being calculated the same way. And for this, you do the same thing where it's products minus reactants, and using the units here, you can see that these values are given with moles being on the denominator. And you remember from the other problem, entropy, change in entropy is supposed to have the units of J over K. So you know that you have to multiply this by moles to get rid of the moles. And now, but before we actually go ahead and do this problem by calculating the change in entropy, I'm going to try to see if, I'm going to show you how to predict or try to predict this problem, because it's asking what the sign, it has to predict the sign. So over here, you look at the reactant side, and if you remember what the moles, these are moles, the coefficients in front of the reaction. So you see here, N2 has only 1 mole in it, and H2 has 3 moles in it. And over here, these are gas. They're all gas, so it doesn't matter. And on the product side, NH3 has 2 moles in it. So if we were going to try to predict, there's 4 moles entirely on the reaction side and 2 on the product side, and the reaction is taking it from 4 moles to 2 moles, so it's decreasing the amount of moles. And if you remember earlier, I said as the moles increase, the entropy increases. So that means as the moles decrease, the entropy decreases. So we're expecting an answer of negative, for the entropy to be less than negative. right here. That's what we're predicting. But let's go ahead and find out by just doing all the writing out all the math and finding out the final answer. And as you can see, I skipped through all the busy work, but wrote it out to show that the moles cancel in every single one of them, and the units you're left with are just joules over K. And like we predicted, it's negative. And that's the end of understanding spontaneous reactions and entropy.